In this video, I'm going to talk about the non-continuum or the random walk tortuosity model in PuMA. Assuming the installation has been complete, PuMA can be run by opening a terminal and typing PuMA, at which point the PuMA window should appear. The first step in determining the tortuosity is going to be generating a computational domain upon which to run the computation. This can be done through either microtomography import or generating an artificial geometry. In this case, we'll generate an artificial carbon fiber preform with 256 cubed, radius of 5 plus or minus 1, or let's make that 4 plus or minus 1, a length of 50 plus or minus 20, and angle variation of 90, 90, and 15, which means this is going to be a transverse isotropic material. We'll use a voxel length of 1 and a porosity of 0.6. As you can see, the domain has been generated, and as per the 15-degree angle variation in the z direction, it has a preferential direction in the z-plane, meaning that in this direction, in this plane, in the xy plane, the fibers are able to orient in any direction completely randomly, whereas in this direction, the fibers only vary by about plus or minus 15 degrees. To compute the tortuosity, go to Material Properties, Tortuosity, and then the previous tutorial discussed the finite difference tortuosity. So this is valid in the continuum, which means that your Knudsen number is very low. So typically, if you're dealing with normal conditions on, at Earth's atmosphere, continuum assumption is fine. Since this software was designed to compute material properties for heat shields on, say, like a Mars reentry or something, we're not always in the continuum. Oftentimes, we're in the transitional or rarefied regime. And in this regime, the typical continuum methods, like this finite differencing method, is no longer valid, and we have to use a random walk model. Now, the random walk model simulates diffusion by assigning a certain mass to a bunch of particles and randomly diffusing these particles via a random walk. The theory behind this is explained a lot more in the user manual, and there should be a forthcoming journal publication on the tortuosity. The theory here gets pretty dense, so I'll really just explain kind of how to run it and what each of these parameters means. The first step is to, much like the finite differencing method, assign a low cutoff and a high cutoff value. Since we did generate this artificially, it means that the void range is between 0 and 127. The next step is the number of particles. Typically, this is taken 10,000 at kind of absolute minimum, and more like 1 million for a solver where you want to have a pretty fine-tuned answer. The total walk length determines the total path that each particle travels during the simulation, which is the same thing as the total walk time of the particles. For the purposes of this, we'll put 100,000 voxels, or maybe 50,000 voxels to make it a little bit faster. The mean free path specifies the average distance that a particle travels in void space before assuming that another collision has happened with another particle. If this value is low, it means that you're going to be in the continuum. So the Knudsen number, which defines whether you're in the continuum or the transitional or rarefied regime, is a ratio of the mean free path to the characteristic length of the material. So if the mean free path is very low, it means that you're going to have a much lower Knudsen number, which means you're in the continuum. If the mean free path, on the other hand, is very high, which we'll do in this case, then you'll end up with a Knudsen number that's very high, meaning that you're in the rarefied regime. In the rarefied regime, you don't have many particle-particle collisions. Pretty much all the collisions that occur are between the particles and the surface. Next is the mean thermal velocity. This will not impact the tortuosity computation. What it will do is impact the calculation of the effective diffusion coefficient, though. Next is the random seed, which is the seed value used for the random number generator of the particles. This can be set to a specific value, like 1, or it can be set to 0, in which case a random number will be used to generate the random seed. If you want the results to be repeatable from one simulation to another, choose a random seed that you remember and you can repeat. The number of threads is for the parallelization. In this case, we'll use the number of physical cores on the machine. In the large workstation we use, that's 44, but in this case we're going to use just 4 threads since we're doing this on a laptop. The collision method is the choice between whether to compute the particle collisions on the cube-Ryle grid, which means just the raw voxels, or on the isosurface approximation, which means the marching cubes or the marching tetrahedra, which represents the surface as a triangles. It's the same triangles that are used for the visualization. In the continuum, meaning that if you have a very low mean free path, both of these will give you the same results. If, however, we're in a situation where it's a high Knudsen number case, meaning the mean free path is very high, the isosurface collision method must be used. The Knudsen tortuosity method, this is explained in more detail in the manual and in the forthcoming publication, but it basically determines whether or not you want to use the name convention that the tortuosity is a constant value as a function of Knudsen number, or the tortuosity changes as a function of Knudsen number, and this really just depends on how you define your characteristic length. So if we then choose variable here, it means that the characteristic length that's used is the mean intercept length, which is the average distance in a free molecular stream between particle wall collisions. And in this case, what you'll end up with is a tortuosity that varies as a function of Knudsen number. It'll have some asymptote that it reaches in the continuum. It, during the transitional regime, will change a little bit, and then it will reach another value in the pure Knudsen regime. For the purposes of this simulation, we'll leave it at variable. The theory here is explained a lot more both in the user manual and in the forthcoming publication, so I won't get too much into it. To run the simulation, say begin calculation, the first thing it has to do is go through and run the isosurface marching cubes to find all the triangles, and then finally it will march the particles, which is what you see here. What's displayed on the plot is the mean square displacement as a function of time. So for every hundredth of the total simulation length, it will compute what the mean square displacement is. The slope of this line is what is eventually used to compute the tortuosity, meaning that for the simulation to be converged, this should be a completely straight line. And often, though, it may look straight but not quite be, so it helps sometimes to take the raw data and process it in Excel or something in order to make sure that it's actually linear. When the final value is finally taken, it will neglect the first half of the simulation and only use the data from the second half of the simulation so that there's less error caused by the solution not being quite converged. And as you can see, the tortuosity is then shown in each direction, with the tortuosity in the x and y direction being very similar since this is a transverse isotropic material, and the tortuosity in the z direction being slightly higher. What's also shown here is the effective diffusion coefficient in meters squared per second, the porosity, the mean intercept length, which is used as the characteristic length scale. This is very important since in the non-continuum regime, so in the transitional and rarefied regime, this tortuosity value here only means something physical when it's used in conjunction with the mean intercept length. This is explained more in the in the user manual exactly how to use these numbers. And then finally, the Knudsen number is shown. And as you can see here, we're pretty much in a free molecular regime since we're very high Knudsen number. So I know there's a fair amount of theory there. As I mentioned several times in this video, it's explained in more detail in other places, but I just wanted to give you guys a brief understanding of how to actually run one of these simulations and approximately what values should be taken in for each of these inputs. And that concludes the random walk tortuosity section of the PuMA software.